Welcome back, students. Today we will continue our discussion into the topic of manipulating polynomials. Specifically, we're going to be looking at a number of examples from chapter 5.3. And then if we have time permitting, we will dive into section 5.4. Let's dive right in. All right, in previous chapters, we were discussing the topic of how we could solve general equations, specifically equations involving linear equations. And of course, we have a process that we're going to work through in order to solve linear equations and or graph linear equations. But in this chapter, we are not actually solving for anything at all. Instead, what we're doing is we are involved in expanding an expression. And when we are asked to expand an expression, all we're doing is we're rewriting an expression in a different way, usually in accordance with the rules of algebra. Similarly, when you're asked to simplify an expression, you're going to use the rules of algebra in order to reconfigure an expression into something that's going to be a bit simpler looking, quote unquote. All right. So in chapter 5.3, problems 35 through 48 essentially just ask you to use the distribution law to find the product of specific polynomials that you're multiplying together. And then for problems 49 through 62, you're specifically asked to use the FOIL method, which they claim is objective 3. And for problems 63 through 72, you're asked to find the product and or difference of two polynomials. Now, what you need to know in my class is that I don't care if you want to call extended distribution the FOIL method or you want to use some other method. I am not grading based on the specific method of choice. And you can put a pin in that, you can put a star in that, write that down in your notes. When I grade your papers, specifically with respect to how you go about solving the problems in chapter 5, I do not care whether you use FOIL or extended distribution or any number of other methods in order to clean up your polynomials or perform polynomial multiplication. As long as your math is correct and as long as the steps are shown in a order and or in a manner that is coherent that I can follow. Like, make your grader's job as easy as possible, right? Make my job easier, and that will generally result in higher marks for the specific student. But I try my best to give all students as many points as I possibly can. And students know that if they ever have a problem with the way I've graded their paper, they can come into my office hours and argue their case, if you will. So, because there's always a possibility that I took off too many points. All right, so let's look at problem 54. Problem 54 is a generic problem where you've got two different polynomials, in this case, two binomials, which are being multiplied together. As you go forward into your next math classes, especially if you decide to take your college algebra course, you will encounter many instances where you have to multiply two or more polynomials together. So it behooves one to really practice this section 5.3. This is one of the more important sections in the entire book because this is going to pay dividends. If you know how to multiply polynomials, you are going to struggle a lot less next semester. Okay, so with that being said, I have a specific method by which I typically multiply polynomials. I'm going to use what's called extended distribution, where I take my first term, in this instance 3z, and just like distribution, I'm going to multiply 3z with the entire quantity that's listed in the parentheses that are next to my first polynomial, 3z minus 2. So in this instance, I'm going to multiply 3z across the entire quantity 4z plus 1. Now, what's interesting here is I'm going to add to this quantity, in this instance, -2, or my second term, multiplied with that second set of parentheses, 4z plus 1. And regardless of how complex my polynomial multiplication problem might be, I'm still just following the same procedure. I'm going to start with taking whatever my first term happens to be within my first set of parentheses. I'll multiply it across the entire quantity that's listed in the second set of parentheses, in this instance, 4z plus 1. And then I'll take my second quantity, whatever that happens to be, in this instance, my -2. And I multiply that across the entire quantity listed in the second set of parentheses for z plus 1. And I'll just do this regardless of how complicated the problem might be, as long as I go step by step, take deep breaths, and don't allow the math to overwhelm me, we should be just fine. In some instances, these problems get rather tedious, so you just have to be aware of that going into it. Sometimes tedium is a part of mathematics. Now, what is a recommended general practice for students is to draw lines from the terms that are out in front to each of the terms inside of your parentheses. What this is going to allow you to do is it's going to allow your eyes to kind of settle in on the individual multiplication operations that you will have to perform. In this instance, you're going to take your 3z, and we have to multiply according to the distribution law with 4z. And then I have to take 3z, and I need to, according to the distribution law, multiply with the second term, 1. And I'm going to do the same thing for -2. I've got -2 multiplied with 4z plus 1, so I need to take -2, multiply with 4z, and I need to take my -2 and multiply it with the +1. Now, what I generally recommend for students is to wrap your negatives in parentheses so that you keep track of your negative signs. The biggest error that I see students doing in this section is just making a mistake with their negative signs. Usually there's no bigger errors than that. Usually students can multiply, usually students can add. And students understand the associative and commutative law, generally speaking, by this point in time. And so the biggest error that you're going to encounter is a student dropping a negative sign at an inopportune moment. So, all right, according to the associative law, we can begin to remove our sequence of parentheses around terms that are all multiplied together. So this parentheses 3z, parentheses 4z, you're just going to remove all the parentheses, and you'll have 3 times z times 4 times z. Okay, and then similarly, you'll have 3 times z times 1, or simply 3z here. Positive and negative becomes a negative, and you'll have 2 times 4 times z. Positive, negative is a negative. You'll have a 2 times 1. Okay, try not to do too many operations at once. If all you can keep track of is removing your parentheses, just remove your parentheses. If all you can keep track of is applying your negative law rules, then just keep track of that. But regardless, go one step at a time. Try to minimize the amount of computations that you're doing for each step of the process. Because now I've got to do the commutative law. I've got to move around my terms, 3 and my 4, and you'll have z and z being multiplied together. 3z doesn't change. 2 times 4 gives me 8, so you should have 8z here. And 2 times 1 gives you 2. 3 times 4 gives you 12. Z times z is z squared. And you'll have, whoopsie, I have 3 apples, but I take away 8 apples, or I owe someone 8 apples. So if I owe you $8, but I have $3 in my bank account, I hope everyone would agree that I still owe you $5. And the -2 doesn't change. So my final answer would be 12z squared minus 5z minus 2. And this would be my answer. Okay. For our second problem, problem 59, we are going to take 5u, or the first term. That's in our first set of parentheses on the left. And we multiply it across the entire sequence of terms on the right, or in the second set of parentheses on the right, more specifically. And then I'm going to take my second term, 6v in this instance, and I'll multiply it across everything on the right. This is the general procedure that we will follow for every single problem in section 5.3. All right. Now we're going to just kind of try to follow. Ooh, I don't know what's going on there. Must have switched to a different marker mode. All right, so you're going to take 5u, you'll multiply with 2u. And we're going to take 5u, we'll multiply with v. We'll take our 6v, we multiply with 2u. And we take our 6v, and we multiply with a v. Again, this particular sequence of letters or the choice of letters for our variables was chosen very specifically because the textbook authors know that V and U, because people will have dyslexia sometimes, will often get confused. And so they're intentionally choosing the U and the V in order to make your job more difficult, in order to make the math more confusing. Naturally, students are recommended to avoid using variables such as U and V together because you're more likely to make a mistake given that people have dyslexia or people are inclined to make transposition errors from line to line where your V becomes a U or vice versa. Nevertheless, at this point in time, we're going to, of course, utilize our associative law and or our commutative law. So we can remove the sequence of parentheses around our 2 and our 2u and our 5u. I almost made a transposition error there. It is in fact a u. And then we've got 5u times v. So that's just going to be 5 times u times v. And I've got 6v times 2 times u. And I've got 6v times v. Okay, now we need to use the commutative law. 5 times 2 gives you 10. You'll have u times u, which should give us a u squared, but we'll hold on that for this moment in time. We've got a u and a v, and I've also got 6 times 2 gives me 12. V times u is the same thing as a u times a v, and I've got a 6 times v times v, or 6v squared. Now, if we go back, we also have a 10u times u, or a 10u squared. So we've got 10u squared plus 5uv plus 12uv. That should give me 17 uv. Don't let yourself get confused by those variables. U times v is just some quantity. So if you've got 5 times u times v plus 12 times u times v, you've got 17 u times v in total. And we've got a 6v squared hanging out in front. So this will be our answer. For problem 71, they've thrown into the mix a number of fractions to try to trip us up and or confuse students. The textbook authors understand that whenever you start introducing fractions, a lot of students will freeze up because they, for one reason or another, struggle with understanding that when we take the rules of algebra and then add in fractions, those fractions just obey the rules of algebra, just like any other number obeys the rules of algebra. So psychologically, students are inclined to think that somehow the math here is going to be more difficult than what we were doing above. But actually, I would say that 9 times out of 10 students are going to make a mistake on the problem above versus this problem once you get into the hang of using the rules of algebra correctly. All right, so what's going to happen here is just like before, we're going to take our first term. We got to multiply with everything in the second set of parentheses. We're going to take our x, we'll multiply with x minus 1/3, just like that. And we're going to add to this the second term in the first set of parentheses, which is negative 1/3, which I recommend people writing like so. And we're going to multiply that across the entire second set of parentheses. Just like that. Okay, just like that. All right, so what are we doing here? We are going to take x, we'll multiply with x, we'll get x times x. We're going to take our x, we multiply with negative 1/3, just like that. We take our negative 1/3, we're going to multiply it with our x value. We're going to take our negative 1/3 and we multiply with with a positive 1/3 rather, not negative, positive 1/3. Just watch out for those negative signs. Don't go too quickly. All right, we got an x times an x. That's going to give us an x squared. We have a positive times a negative. That should be a negative. X times 1/3, that will be 1/3 x. Positive and negative is a negative. 1/3 times x is just going to be 1/3 x. And negative and a positive is going to be a negative. Positive and a negative will be a negative again. You've got 1/3, whoops, 1/3 times 1/3. Just like that. And if you want to go ahead and do the fraction multiplication, you can. Either way, x squared is just x squared. I owe you 1/3 of a banana, and I owe you another 1/3 of a banana. In total, I owe you 2/3 of a banana at the end of the day. Okay. I know that's a little bit frustrating for a lot of students, but if you have negative 1/3 x minus 1/3 x, this is not really any different than saying negative 1/3 minus 1/3, okay, which would just be negative 2/3 because you have to add across the numerator or subtract across your numerator. So in this instance, you owe someone 1/3 of a dollar, and then you owe them another third of a dollar. So in total, you owe 2/3 of a dollar. Well, the same thing is true when you've got negative 1/3 x minus 1/3 x. The x doesn't really do anything. Recall that, by the distribution law, your x could actually be pulled out and you'd have negative 1/3 minus 1/3 inside of your parentheses. So at the end of the day, when you've got that negative 1/3 x minus 1/3 x, you're going to have just negative 2/3 x. And that's all we have to worry about. Now, a much simpler situation occurs whenever you've got your fractions multiplying with one another. Remember, it's just all you have to do is multiply fractions across the top and across the bottom. That is it. When you add, you need to make sure that you have a common denominator. But when you multiply fractions, you multiply across the top and across the bottom. 1 times 1 is 1. 3 times 3 is 9. So at the end of the day, x squared minus 2/3 x minus 1/9 is going to be our winner chicken dinner. This is our answer. Going down to problem 85, we start to encounter a situation where we really need to understand what we are doing when we use the FOIL method. And this is why I don't teach the FOIL method at all, because FOIL is a very limited version of extended distribution. All we're doing when you FOIL, or when we are multiplying out our terms using extended distribution, is we are saying that when we have these two polynomials multiplied together, we have a situation where each of the terms being added or subtracted in our first set of parentheses needs to be multiplied by the entire second quantity. So in this instance, you had an x and a negative 1/3. Both of those had to be multiplied with that x plus 1/3. But here in problem 85, we've got 2y squared minus 6y plus 1. So we have three quantities in our first set of parentheses. Each one of these quantities has to be multiplied in total with the second term. So you're going to take this 2y squared, you have to multiply it with y minus 3. And then, of course, we have to add to this your second term, negative 6y, that will also be multiplied against y minus 3, again, according to distribution law. And we've got to take 1 and multiply it with y minus 3. So it's not that this problem is necessarily more challenging than the previous one. It's just like, now that we add more terms, what do we have to do? Well, we have to just continue this general principle of extended distribution. Okay, cool. So now we're going to use the distribution law, or rather, said another way, our distribution law will kick in on an individual basis. We'll take our 2y squared, we're going to multiply it against y and a negative 3. So you're going to have 2y squared times y plus 2y squared times negative 3. Watch out for those negatives. Now, you're going to add to this your 6y times y. So you've got negative 6y times a y here. You're going to add to this a negative 6y times. So what are we doing? We're going to multiply it against a negative 3. And then 1 times anything is just that something. So if you wanted to just bring down y minus 3, that's fine. If you wanted to do distribution here, you got 1 times y plus 1 times negative 3. It doesn't really matter. That's going to be cleaned up in a second in a single step anyways. All right, so we got 2y squared times y. Well, y squared times y gives you y cubed. Positive and a negative, of course, gives you a negative. We've got to remember our negative laws. And of course, we'll have 2 times 3 times y squared. Positive and negative is a negative. You'll have 6y times y is y squared. And you got a positive and a negative and a negative. Well, negative and a negative is a positive. Positive and positive is a positive. So we'll have a positive 6 times 3y. Well, plus, well, we've got a positive and positive, which is just a positive. 1 times y is y. Positive and a negative is a negative. 1 times 3 gives you 3. So at the end of the day, we should be able to clean up our polynomial expression just like that. Pause the video and make sure you understand what I'm doing at each and every step. Okay, it doesn't do you any good to watch these videos if you don't understand every single step that I'm going through. Don't just copy down and then hope that by osmosis, you're going to be able to approach the homework problems, really understand what I'm doing in each and every step of this process. Okay, but let's continue. So now you've got a 2y cubed. There's really nothing we can do with that at the moment. But we do have a negative 2 times 3 is 6y squared minus 6y squared. 6 times 3 gives us an 18, so it should have a positive 18y. And this is going to be added with a y minus 3. Okay, cool. So now it really looks like we can start to clean everything up. Of course, the 2y cubed just is 2y cubed, but if I owe you $6 and then I owe you $6 again, I should owe you $12 in total. So if I've got negative 6y squared minus 6y squared, I should have in total negative 12y squared. And for the same reason, if you've got $18 in the bank and then you add $1, you should have $19 in the bank in total. And then the minus 3 doesn't change. So there's our answer. Okay, for problem 91, all you're going to be doing is you're going to use the distribution law for this first term, and you're going to want to distribute it across the second set of parentheses here. So you're going to have a negative 1/2 x. We're going to multiply it with 2x. We'll have a negative 1/2 x times 6. And that's going to be the first thing that we'll do. But the real trick of this problem is to recognize that once you do this multiplication, the question, of course, becomes, what do you do with this remaining x minus 3? And the issue is that when you did this distribution process, you actually have all of these terms inside of its own set of parentheses, and the x minus 3 doesn't change. So it's not that you've got x minus 3 multiplied with that last term, negative 1/2 x times 6, but rather the x minus 3 is going to be multiplied with the product that is produced when you do the distribution law. So remember, the distribution law is producing a product. It's like taking 3 times 12 and asking how much do you have left over? Okay, well, if you had 3 times 12 and then you multiplied it by 8, okay, you still have to do 3 times 12 or 12 times 8, but the extra term that you're multiplying something by, that doesn't somehow just magically disappear. So this x minus 3 doesn't just magically disappear because we decided that we're going to use the distribution law to multiply negative 1/2 x across 2x plus 6. That's still there. And the question, of course, is, does it make sense for the x minus 3 to be multiplied with the last term only, which is going to be the mistake that a lot of students make? Or does it make sense to multiply it with the entire product? And of course, for the same reason that you would take, if I had 3 times 12 times 8, and I decided to multiply 3 times 12 first, I still have that 8 remaining that I need to multiply with the product of 3 times 12. That's going to be what happens here. So in this instance, we got to, of course, clean up this negative 1/2 x times 2x. So, of course, you've got a negative and a positive, which we know is going to be a negative. We could go ahead and remove our parentheses if that makes our life a little bit easier, at least around the first term. You've got a positive and a negative, which is a negative, and you have a 1/2 times x times 6. Of course, nothing happens to the x minus 3. So now is where the magic happens, because you've got to use the commutative law to group like terms together. So I'm going to take the 2 that is out in front of my x here for this first term inside my parentheses. I'll move it forward next to the 1/2. And I'll do the same thing for my second term. I'll move my 6 next to the 1/2. So you've got 6 times 1/2. And then x minus 3 doesn't really change. So you've got this setup more or less. Now, negative 1/2 times 2 is just going to be, well, 2 times 1 is 2, divided by 2 is just 1. So you've got 1 times x. 6 times 1/2 is just 3. X doesn't change, and you've got an x minus 3 left over. X times x is x squared. Positive and negative is a negative. 1 times x squared is just x squared. So you got an x squared minus 3x times x minus 3. Okay, brilliant. Now, if you want to use the extended distribution, we're going to take our first term, which in this instance is the negative x squared, and we'll multiply it across x minus 3. And we'll add to this the negative 3x, or our second term, multiplied with the entire second set of parentheses, x minus 3. All right, and so of course we've got to do the multiplication individually, just like so. We're going to take our negative x squared. We got to multiply with x. We got to take our negative x squared. We multiply it with negative 3. We take our negative 3x. We multiply it with a positive x. And we take our negative 3x and we multiply it with a negative 3. Okay, so at this point in time, we're going to just focus on cleaning everything up. Negative and a positive is a negative. X squared times x gives us x cubed. Negative and a negative is a positive. X squared times 3 is going to be 3x squared. Positive and negative is a negative. 3 times x is just 3 times x, but x times x gives you x squared. So now you have a positive 3x squared minus 3x squared. Interesting. And you've got a positive and negative, which is a negative. But now what's interesting is you've got a negative times a negative, which gives you a positive. Because remember, you've got this negative 3 and a negative 3. So that's going to be definitely a positive number. And you've just got 3x times 3 at that point in time, because negatives go away. All right. Cleaning this system up, your negative x cubed doesn't really change. But you'll note that you've got a 3x squared minus 3x squared. So that would add to be a 0x squared if you wanted to, write it down. You'd have a 0x squared. And then what happens here is you've got a 3 times 3. So by the commutative law, 3 times 3 gives you 9. And you'll be left with the 9 times x. All right, so now all we have to do is we are going to take our negative x cubed, but we're adding to this the 0x squared, which of course is just 0. So you could say this is 0 plus 9x, but 0 plus anything is just that something. So you've got negative x cubed plus 9x, and that's pretty much as good as we can do. Oops. Okay. Now, moving into section 5.4, what we're going to be learning about is what happens when we have what are known as negative exponents. What we learned last week is that, just as a basic definition, when you take a number and you raise it to a power, such as taking x, which is just some number. I don't know what x is. You don't know what x is. X is just some number. And we raise it to a power in a very basic sense. What's going to happen is you'll just have that number multiplied by itself that number of times. So if you raise it to the n power, you'll have x multiplied by itself by whatever n happens to be, sort of that many times, said another way. But the question that we're going to try to answer in this lesson is, suppose I raise x to a negative n. What happens here? Can we even raise a number to a negative exponent at all? And if so, what does that look like? What occurs? What happens? And so the answer, of course, is yes, you can raise a number to a negative exponent. But to understand what's going to happen takes a little bit of mental gymnastics, shall we say. First of all, we need to understand what happens whenever you have exponents that are within the context of a fraction. So what do I mean by that? I mean, suppose you have, say, a situation or a scenario such as, we'll use the number 2, because 2 is something that we can all relate to. We know how to conceptualize 2 of something. So if I had a number like 2 to the 5th, and I was to divide this by 2 to the third, the question would be, what would happen here? And of course, to make this a little bit of a nicer problem so that we can see the pattern that emerges, I'm not just going to take 2 to the sixth and divide it by 2 to the third. I'm actually going to start with 2 to the second, 2 to the sixth, and I'll divide it by 2 to the second in order to give myself enough examples in order to establish a pattern. So if I took 2 to the fifth and I divided it by 2 to the third, I'd only have a couple of examples to work with. But if I take something that's a little bit bigger, like 2 to the sixth, and I divide it by 2 to the second, I should be able to establish a pretty nice pattern that occurs. Of course, just as a basic definition, when you've got 2 to the sixth, that's going to be 2 times 2 times 2 times 2 times 2. Or said another way, 2 times itself 6 times. And what we do know is that 2 squared would be 2 times itself 2 times. That's according to just the basic definition of exponents. So if we rewrote this fraction 2 to the sixth divided by 2 squared, or 2 raised to the power of 2, on the top of our fraction in our numerator, we should have 2 times 2 times 2 times 2 times 2 times 2 on top. In our denominator, rather, we should have 2 times 2 just hanging out. Now, of course, one strategy for being able to simplify this would be for us to multiply all of our 2's together and to figure out what the top quantity happens to be relative to the bottom quantity, or if the bottom quantity just kind of, erases for some inexplicable reason, and then try to establish a pattern that way. But what we're going to do is we are actually going to exploit the rule of prime factorization, or dividing out prime terms that we learned in Math 900 or in our lower level algebra sequences back in high school. And what that just means is, if you had 100 divided by 10, what we know about 100 is that we could rewrite 100 as 10 times 10. So you'd have 10 times 10 divided by 10. And at this point in time, if you guys recall, you can cross out a term that exists in your numerator if that term also exists in the denominator. Because what happens when you've got 10 times 10 over 10 is that it's the same thing by just using the rules of rearranging fractions as 10 divided by 10 times 10 over 1, or put simply 10, which would be this 10 here is this 10. Of course, 10 divided by 10 just gives you 1. So at the end of the day, you have 1 times 10, or just 10. So if we skip the process of dividing out our fractions, and we just recall that you can cross out like terms if those terms exist in the numerator and the denominator, then we should be able to cross out the prime factors too, and these prime factors too. And so at the end of the day, we are then left with 2 times 2 times 2 times 2, or said another way, 2 raised to the fourth power. Now, if you did want to think about dividing out your 2's, then what would have happened is you just have 2 divided by 2 times 2 divided by 2 times 2 times 2 times 2 times 2. And of course, 2 divided by 2 gives you 1. 2 divided by 2 gives you 1. So at the end of the day, you have 1 times 1 times 2 times 2 times 2, or just 2 times 2 times 2. Personally, I like the shortcut at this point in time, because that way I don't have to write out a bunch of fraction expansions. But if you guys, need to practice with the fraction expansion just to get a hold of it, or to, practice with it, essentially, go ahead and do that, okay? So the strategy that I'm going to try to use is what is known as induction. So I'm going to try to, with the method of induction in mathematics, I'm going to try to essentially give myself a simple example that we all can kind of agree to if we understood the rules of algebra. We understood the rules of algebra, or if we were to multiply out 2 raised to the 6th and then divide it by 2 squared, at the end of the day, we should be left with a number that is the same thing as 2 raised to the fourth. Okay, even if we were to do this manipulation of the fraction in a totally different manner, we should all agree at the end of the day we'll be left with 2 to the fourth. So because we can agree to that, what I'm going to now do is I'm just going to increase the exponent of my bottom term, and we'll see what happens. So I'm going to take 2 to the sixth. If that doesn't change, but what we're going to see is we're going to see what happens if I raise the power of my bottom exponent. And so now instead of 2 to the second power, we're going to have 2 to the third. But what we're going to try to do is just establish if there exists some sort of a pattern as I keep increasing my exponent. And maybe that pattern has something to do with negative exponents if you guys haven't already found out, or if you guys don't already know. Okay, so just like before, what we're going to do is we're going to start by expanding 2 raised to the sixth. And what we know is that 2 to the sixth is going to be the same thing as 2 times 2 times 2 times 2 times 2 times 2, or 2 multiplied by itself 6 times. And then this time we are going to expand 2 to the third, which we know should be 2 multiplied by itself 3 times. And just as before, we can start crossing out quantities that are the same thing or that are in common between your numerator and the denominator. So we should be left with 2 times 2 times 2, or by the definition of exponents, because I've got 2 multiplied by itself 3 times, I should be left with 2 raised to the third. And so now we can just keep doing this process. We're going to take 2 to the sixth and we'll divide it by 2 to the fourth. We've got 2 times 2 times 2 times 2 times 2 times 2 on top. And we've got 2 times 2 times 2 times 2 on bottom, or 2 raised to the fourth on bottom. We cross out terms that are in common between the numerator and the denominator. So boom, 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 boom. You are left with 2 times 2, or 2 squared. And of course, we can keep doing this however many times we want to. However, after about 3 times, we should be able to establish some sort of a pattern. And so what we'll now do is we'll take our input into this process and the output, and we're going to line these up in order to try to see if there may be a pattern in our data. So we've got 2 to the sixth power divided by 2 squared, and we said that that resulted in 2 to the fourth. So we'll write out 2 to the sixth divided by 2 squared, and we said that gave us 2 to the fourth. And then we upped our exponent in our denominator. We went from 2 squared to 2 cubed, and that resulted in us obtaining the answer 2 to the third. And then the last time we took 2 to the sixth and divided by 2 to the fourth, and that gave us 2 to the second power. Okay. We are now going to ask ourselves the question, what is the pattern? I go from 2 to the sixth divided by 2 squared, and I get 2 to the fourth. I go from 2 to the sixth divided by 2 cubed, and I get 2 cubed. I go from 2 to the sixth divided by 2 to the fourth, and I get 2. So if you were to line up your values, in this instance, the exponents, and we're just going to play a game of fill in the blanks, where the potential answers are that you've got a relationship where you could put a plus sign in the blank between the 6 and the 2, and the 6 and the 3, and the 6 and the 4, or you could put a minus sign, or you could put a multiplication symbol, or you could put a division symbol, and you're just asking yourself, what is the relationship between 6 and 2 and the number 4? Is that an additive relationship? If you take 6 and you add 2, do you get 4? And of course, you would say, no, 6 plus 2 does not give me 4. And in fact, 6 plus 2 gives me 8, okay? Similarly, 6 plus 3 doesn't give me 3, and 6 plus 4 doesn't give me 2. Then you say, okay, well, is this relationship multiplicative? Well, 6 times 2, that doesn't equal 4. 6 times 2 is in fact 12. And 6 times 3 is not 3, and 6 times 4 is not 2. But then you ask yourself, well, does division work? 6 divided by 3 gives me 2. And of course, that is in fact not going to be the same thing as 3. So at the end of the day, by the process of elimination, the only operation which seems to be able to link these exponents and the output of this equation is subtraction. If I take 6 and I subtract 2, I get 4. If I take 6 and I subtract 3, I get 3. If I take 6 and I subtract 4, I get 2. And what that tells us is that anytime you have a number raised to an exponent and it's divided by the same number but raised to a different exponent, you may take these terms and subtract the bottom term from the top term. This is called the exponent subtraction rule or law. But here's the question, gang. Here's the question now. What happens if I take 2 to the 6th and I divide it by 2 to the 7th? Well, according to the exponent subtraction law, which we agreed to earlier, what we said was the only way that we can relate these exponents to what is actually happening when we perform fraction simplification is that really the exponents are subtracting one from the other. So we're taking the 2, we would have to take the first exponent 6, and we would have to subtract 7 from 6 according to this exponent subtraction law. And that would, of course, give me a 2 raised to the -1. But what does that actually mean? What does that mean? So if we took 2 to the 6th and divided by 2 to the 7th, and we go ahead and expand 2 to the 6th, we're going to get 2 times 2 times 2 times 2 times 2 times 2 on top. And on bottom, we have 2 times 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 1, 2, 3, 4, 5, 6, 7. Okay, 7 times. So I think we're good. And then we start crossing out terms that are in common with each other. We're going to cross out these 2's, got another set of 2's, and another set of 2's, and eventually you just start crossing out everything that you've got. And of course, you're left with a 2 in the denominator, but you'll note that everything in the numerator seems to be crossed out. So the question, of course, that students are going to have at this point in time is what happens to the numerator? Because if you just wrote a 0 in the numerator, that would be an issue because 0 divided by 2 gives you 0. So a lot of students would get stumped. And at that point in time, I would ask students, go ahead, why don't you expand out the fraction using the rules of fraction division. So if we just take our initial fraction, we go ahead and expand everything out. What you'll see is by the rules of fraction multiplication, you'll be left with a bunch of 2's divided by 2's, which of course just gives you a 1. So you'll have 2 divided by 2 gives you 1. So you'll have 1 times 1 times 1 times 1 times 1 times 1. But what's left over is you actually have a 1/2 left over. So just remember, students, that it's not like our numbers disappear as if by magic when we're doing these fraction reduction steps. We're just, using a shortcut. So at the end of the day, the shortcut needs to obey the rules of algebra. It's not, something that we're making up on a whim, if you will. So it's not like our 1 just disappears. It's that, what we're using is we're using a shortcut here. So, all right. Now, just like before, in order to truly understand what's happening with these negative exponents, we will of course, just begin to increase the exponent in our denominator and try to figure out if there is, in fact, some sort of a relationship that we might have. You'll recall that 2 to the 6 divided by 2 to the 7, we found that that was equal to 2 to the negative 1, but that 2 to the negative 1 was also equal to 1/2. So now what we're trying to do, our goal is we are going to establish a relationship for a number raised to some negative power. If I take a number A and I raise it to a negative power, what is that equal to? Of course, we're using a number that we're all familiar with in order to accomplish this goal, in this instance, the number 2, but I could have picked any number that I want, and presumably, whatever number I happen to choose is going to obey the rules of algebra, so that needs to comport itself with whatever we decide happens to be the case for our exponents as well. So, okay, so now we'll take 2 to the 6th. We're going to divide it by 2 to the 8th. By the fraction subtraction rule, we know that we need to take the top exponent, which is 6, and we'll subtract it from the bottom exponent, which is 8. So we'll have 2 raised to the 6 minus 8, or 2 to the negative 2. Simultaneously, if we were to expand out this expression, you've got 2 multiplied by itself 8 times in your denominator. 1, 2, 3, 4, 5, 6, 7, 8. And you'll have 2 multiplied by itself 6 times in your numerator. When you go ahead and you cancel terms, you'll now have 1 divided by 2 times 2, or 1 over 2 quantity squared. Interesting. Just like before, to establish a pattern, I need to give myself enough instances to actually see if there is a pattern. So we'll increase the denominator by an exponent of 1, or a degree of 1. So instead of 2 raised to the 8th, I'll now have 2 raised to the 9th power. And just like before, we can use the exponent subtraction law. 2 to the 6th divided by 2 to the 9th is the same thing as 2 raised to the 6 minus 9, or 2 to the negative 3rd power. And just like before, if I actually wanted to know what that means to me, I can go ahead and expand out the expression. So I should have 2 multiplied by itself 9 times in the denominator, and 2 multiplied by itself 6 times in the numerator. Just go ahead and double check that indeed you've got the correct number of 2's. 3, 4, 5, 6, 7, 8, 9. Okay, cool. So it looks like we're good. And now we can divide out terms. So 2's on top and bottom eventually divide out. You're left with 1 over 2 times 2 times 2, or 1 over 2 cubed. Brilliant. So now all we have to do is try to establish a pattern. We said 2 to the negative 1st power was the same thing as 1 over 2. 2 to the 2nd power, negative 2nd power, was 1 over 2 squared. And of course, 2 to the negative 3rd power was 1 over 2 cubed. So the question that students should have at this moment in time is, what is the pattern, if any, that we might be dealing with here? Well, if we permit ourselves to, instead of writing 1 over 2, to write instead 1 over 2 to the 1st power, it becomes very evident what the pattern happens to be. We are essentially flipping the number into the denominator and raising it to a power. In fact, that's exactly what we're doing. And it's for this reason that we call 2 raised to the negative 1 an inverse of 2. Because it's obeying the same rules that we come to associate with a multiplicative inverse, if you will. But that, of course, being neither here nor there at this moment in time, it's just kind of an interesting side note. Now, I hope everyone would agree that if you have a number raised to a power, and I think I was using the letter n before, so we'll just have a raised to a negative n, if you will. What seems to be the pattern here is that we're just flipping the number into the denominator of a fraction. And we are changing the sign of that term. So when you've got 2 to the negative 1, you flip it into the denominator of the fraction, into the bottom component of a fraction, and you flip the sign to being a positive 1. When you have 2 to the negative 2, you are flipping the number into the denominator of the fraction, and you're changing the 2 to the negative 2 to a positive 2. Very good. This is the negative fraction. Sorry, not negative fraction, but negative exponent law. We'll call it part 1, because there are indeed 2 different forms of the negative exponent law. Go ahead and pause the video right here and write this down into a cheat sheet of some sort, because we are going to now look at the second negative exponent law, and that would be what happens if you have a number in the denominator that has a negative exponent. Is there perhaps a rule that we can use in order to clean this up? In fact, there is. And there's 2 ways of approaching this problem, or a number of different ways of proving or demonstrating what happens whenever you have a number that's in the denominator of a fraction raised to a negative exponent. On the one hand, just like before, I could give myself a bunch of cases to where I need to figure out what exact, I basically force myself into finding a pattern. But alternatively, we could just use the rules of algebra as well as the definitions that we're provided with in order to determine what has to be true. And so in this instance, it's actually easier for me to just go ahead and use the negative exponent law as well as the rules of algebra to prove what has to happen. So in this instance, say you have a raised to the negative m, okay, that's in your denominator. Or if we want to be consistent with the above, we'll say a to the negative n, whatever. Doesn't really matter. Then what we know from the previous problem is that whenever you have a number raised to a negative power, it's going to be the same as taking the number, flipping it into the denominator, and raising it to a positive power. So if you have 1 over a raised to the negative n, that's going to be the same thing as, according to the negative exponent law, 1 over 1 divided by a raised to the positive n. Now, here's the deal, gang. We have to remember what happens when you take a fraction and you divide it by another fraction. That's why we spent basically 2 weeks on the first chapter, because every single rule of algebra is important. If you guys remember, when you divide a fraction by a fraction, all you have to do is flip the bottom fraction. Okay, so we flip and we multiply the bottom fraction with whatever the numerator happens to be. In this instance, that's exactly what's happening. We've got a 1 in our numerator, but we take our denominator, we flip it, and you multiply. So 1 over, I'm sorry, you'll have a to the n over 1, which is just a to the n. And of course, that's multiplied with 1, so you are left with a to the n at the end of the day. Conclusion: 1 over a to the negative n is always going to be equal to a to the positive n. And of course, this rule we can use in a number of different ways, in a number of different contexts. But it's just useful for us to be able to remember that it indeed exists, and that we can use it at any moment in time as it becomes convenient for us to do. A final rule that we need to look over, or we need to remember, is simply what happens when you have a fraction raised to an exponent. So if you have an a divided by b raised to an n power, what's going to happen here. Because a lot of the problems in section 5.4 are going to exploit this particular result or this particular circumstance. And what we talked about here earlier when it came to the product law is actually what's going to be very, very similar to what goes on in this particular instance for a number of different reasons. We'll get to that probably in class, but nevertheless, when you've got a fraction and you raise it to an exponent, such as is the case here, what happens is going to be very, very interesting. If you recall, when you have a regular number raised to a power, all you're going to do is you multiply that number by itself that many times. So x raised to the power of n will be x times itself n times. When we have a over b raised to the n, that is going to be the same thing. We're going to have a over b times a over b times a over b times a over b times itself in times. But what happens is pretty interesting. Because a over b is multiplied by itself in times, and you multiply your fractions across the numerator and across the denominator, you'll have a multiplied by itself in times, and you'll have b multiplied by itself in times. So our conclusion is simply that a over b raised to the power of n is going to be the same thing as a to the n divided by b to the n. Let's have a couple of problems or examples that demonstrate how this works. Suppose you have 1/3 raised to the 7th power. If you have 1/3 raised to the 7th power, of course, you could expand out this expression. You'd have 1/3 times 1/3 times 1/3 times 1/3 times 1/3, right? 7 times. And of course, you'd have 1 times 1 times 1 times 1 times 1 times 1, 1, 2, 3, 4, 5, 6, 7, and 3 times 3 times 3 times 3 times 3 times 3 times 3 on bottom, and you get 1 over 3 to the 7th, because 1 times 1 is just 1. So 1 times itself 7 times will just give you 1, and you'll have 1 divided by 3 times itself 7 times, or 3 to the 7th. So that would, of course, be your answer. However, while it's comforting to know that we can expand out a fraction that might be raised to an exponent, if we have a slightly more challenging problem, if we have something like 2 to the 3rd, 2 divided by 3 raised to, I don't know, the 105th power, what we need to remember is that all we're going to do is we're going to take the top number, raise it to whatever the exponent happens to be, and then we take the bottom number and raise it to whatever the power of the exponent happens to be. So you'd have 2 raised to the 105 divided by 3 to the 105. Now, the same is true if you had a negative exponent out in front of your fraction. If you had, say, a 2/3 time raised to the power to the -2 power, if you will. This would be the same thing as 2 raised to the -2 over 3 to the -2. Now, of course, whenever you have numbers that are raised to a negative power, what the textbook likes is it likes if you simplify your expression in such a way to where you remove all of the negative exponents from the expression itself. And so what we remember is that whenever you have something raised to a negative power, you just kind of flip it into the bottom of your denominator. So 2 to the -2 should become flipped into the denominator. It'll be 2 to the +2, and vice versa. Whenever you have a number that's in your denominator raised to a negative power, you can flip it into the top of your expression. So 3 to the -2 can be flipped into the numerator, and it would be 3 to the +2 power. Okay, guys, we will go over many, many more examples when we are in class, but that's pretty much all I've got for you. Take care.